So continuing forward, let me start talking about blackbody radiation. So what is blackbody radiation? But I'm not going to call it blackbody yet. I'm going to call it number one. Blackbody is a body that is an ideal absorber and hence an emitter of all radiation incident on it, which means all radiations with all frequencies, all angle of incidences, all wavelengths. So what are the different kinds of radiation that could be incident on it? Its angle of incidence may change. Its wavelength may be different. Obviously, if its wavelength is different, its its color will be different. It could be radio waves, it could be it could be X-rays, it could be gamma rays, whatever else radiation there is, it will absorb everything, which means it will also emit everything. What we also know about blackbody is that no other object at the same temperature can emit more radiation than a blackbody, which means both in terms of wavelength and direction. So practically, what is a blackbody? A blackbody is a box with a tiny aperture on one side, which allows for radiation to be incident on it, and it also allows for radiation to leave the blackbody. And inside the blackbody, once the radiation goes in, it gets trapped. Okay, that's what a blackbody is. Also, a very good example of how people have formed black boxes, is by a series of sharp edges of a stack of razor blades. So the array that is formed effectively traps the light between it. Now, what was the problem? The problem was that the physics at the time could not explain this phenomenon. So I have just told you that the blackbody should absorb all wavelengths and emit them all at once, right? So it doesn't mean how much it absorbs and how much it emits. Problem was that the 19th century physics at the time did not have a formalism that could incorporate all of this. So blackbody led us to the development of quantum mechanics. An entire field was developed just to explain this blackbody with some soot in it. Okay, so the explanation and understanding of the experimental results that were observed for blackbody. I'm just going to write BB Everybody okay with me writing BB instead of the whole black body? Cool. Radiation led to the development of quantum mechanics. And the correct form for the spectral, just write this down and I'll explain it, excitance, m lambda of a black body was first derived by Max Planck in 1900. And he did it by postulating the quantization in the process of absorption and radiation by the black body. And the formula that he derived was given as m lambda 2 pi hc squared over lambda 5 1 over EHC over lambda KT minus 1. Okay, pause for a second after you've written that down.
Is lambda to the fifth?
Yep. Lambda to the fifth. He derived this formula by studying, you know those graphs that are on your worksheet? Yeah, there's one but with multiple lines on it, right? Look at that and then look at this graph. This is this formula. Of course it makes sense, right? It's so obvious. It's not obvious at all. Right? I want you to put it in a box. Put it in a circle, I don't care. Where m lambda is the spectral excitance. Do you remember the word excitance? It was defined as power per unit area per unit wavelength. And this is not done yet. This is power per unit area per unit wavelength of the interval emitted by a source. In this case, a black body. Also, do you see on your papers that there are multiple graphs? This just explains one of them. What are the rest of them? The rest of them are temperature dependent. So each of these graphs actually changes when you change the temperature, which he incorporates here in his equation by e to the power, the exponent hc over lambda kt. You see it? That t goes in there. And that T is calculated in Kelvin. Okay, so then the other thing that simple equation helped explain was your graph. If you guys want to draw it, I'm going to try to draw these, but they're not going to be good, so that's why you have the notes. But you have to see how it looks like, what they do. And people who have taken modern or who plan to take modern, you guys will do this in detail. But for now, this is the fact I want you to be aware of. Each of these curves correspond to a different temperature. right? So as the temperature, so this one corresponds to the temperature of about 3,000 K. This one corresponds to T equals 4,000 K. This one is like T equals 5,000 K. Of course, it's not drawn to scale. This one is T equals 6,000 K. Our sun is what, 5,800 K? Don't remember.
5,778.
So I'm right. So it's about 5,800.
Not what I got. I thought mine Fahrenheit.
No, not in Fahrenheit, in Kelvin. So I'm thinking, that's what I remembered. I remembered it was like very close to 6,000. So do you see the peaks shifting? What is it going towards? This is the wavelength. And this is m of lambda. So as you increase the temperature, your peak spectral emittance goes towards the lower and lower wavelengths. And that is also the basis for astronomy. That's how they discover how hot a star is, by knowing the light that's coming from it. It's all connected.